Good afternoon, everyone. Welcome to CSL Student Conference. My name is Bihan Wen, and today I'm going to discuss about my thesis work on low-quality image and video reconstruction using data-driven approach. And this talk is based on joint work with my lab colleagues and my PhD advisor, Urbana-Champaign. So actually last week, I was registering for a CSL Student Conference, and I saw this beautiful banner showing on the website, and it has a wonderful picture of our CSL building. The conference title, logo, everything was perfect. But from my perspective of view as a researcher in image processing, I see one of the biggest challenge in image processing field, and that is what are the image pixels blocked by these words. And this is actually has a name. The name is actually image impeding. It's a problem in image processing, and that's not an easy problem. Well, let's see. Here's an example. So we have CSL blocked our CSL building, and so let's guess what could be possibly behind that CSL, right? So in fact, it can be actually anything, right? So it can be anything because we are pretty much guess the unseen pixels, and if without any additional information, this is actually a earpose problem in. And I mean, pretty much like you can have infinity many solutions without any additional prior. And what we do want here is like we want a good model for the underlying true image so that we can possibly exclude those wrong answers, wrong guesses, because those guesses won't fit into that data model for the ground true image. And then, well, then the question is what kind of model we want. I mean, what kind of property we have for the true images. Well, there are many, but one well-known one is called the sparsity. And when we say a signal is sparse, it basically means most of its coefficients are equal to zeros. And here we're not talking about spatial domain sparsity because, as we know, natural images are pretty much dense in spatial domain. However, they can be sparse in some transform domain. One of such type of transform is the discrete Fourier transform. I think in college, all of us know that sinusoids signals can be perfectly sparse under the discrete Fourier transform. And the other famous example is the discrete cosine transform, DCT, which has been widely used in image processing. So, then the next question is why do we need such a model? How can the model help us to distinguish, the data, the image we want, and then the possibility corruptions? And we can have an example, for example, the noise corruption, which is commonly encountered in the image processing problems. So we have synthesized the IID white Gaussian noise, and then we look at what's the coefficient in the 2D DCT transform domain. It turns out to be also an IID white Gaussian noise, so it's not sparse at all. But natural images are actually highly sparse in the DCT coefficients. So this means maybe it's hard to tell the difference in the spatial domain, but it's very easy to distinguish the natural image from the possibly corruption in the DCT domain. So this is a tool for us to tell the difference and exclude the wrong answers. And then let's look at how actually we apply the transform, transform model. So what here is actually an illustration of, we have a signal Y, the data sample, or for example, the image patches we are dealing with here. And here the W is actually the transform, which is a matrix. And when we apply the transform, it's pretty much like we multiply the matrix W to Y, and then we get something sparse, X, which is our sparse coefficient, plus some small arrow eta here. And these are the notations. And then, well, the procedure of calculating the sparse code X is called the Sparse Coding in the transform domain, and it's actually very cheap by simply half thresholding. The reverse way, knowing the sparse code, knowing the transform to recover the signal Y is also simple by a simple least square estimate. And then the question here is, the question we wish to ask is this DCT, DFT, which are widely used, the optimal sparsifying transform or we can find? Well, the answer is no, because they are generally good transform. But if we are interested of a specific type of data, it turns out that why not we just learn the transform directly from the data to give us something optimally sparse. So that's the problem we are looking at. We are looking at this doubly blind problem where the transform is going to sparsify data is unknown, and plus the sparse coefficients for the signal is also unknown. So this is a much more difficult optimization problem than the conventional sparse coding, and we name this problem as transform learning problem. So due to time limit, I can only give a quick introduction of the most basic form of square transform learning, and that is the P1. Here we kind of jointly minimize this objective function over two things. One is the transform W, and then the sparse coefficient X. Y is the signal we have. And well, the first term is the modeling error to match like how well the data will fit into the transform. The second term is a regularizer, which prevents the trivial solution and bad conditioning of the learned transform. I just want to point out that this basic form has several limitations, which I cannot cover one by one. But I want to mention that we have various follow-up works to address each of these drawbacks. For example, we have these octobursts to kind of learn a union of transform instead of one to handle those very diverse textures. We have this online transform learning work, which deal with the streaming data, like videos and like the temporally sequentially arriving data. And then we have this stroller, which is a transform learning plus additional low-rank regularization, and the FRIST, which is to learn the flipping and rotation invariant transform. So I cannot have time to cover all of them, but if you are interested, feel free to shoot me an email. I can provide more details. But I do wish to give you an idea and the flavor, like how we can use this tool, the transform learning, to in this ill-posed image reconstruction problem. We basically use the learn transform as an image regularizer to tell us which is the right solution, which is the wrong solution. And the way we do that is, say we have a degraded or noisy measurement, like the noisy images. We actually take out the patches and we feed into our transform learning algorithm box with these patches as the training samples. And then we do three things. We iterate through these three major steps. That is the sparse coding step, which is to find the sparse code, transform update step, and also the image reconstruction. You may probably want to iterate several times until we observe the transform converge eventually. And then the reconstructed image will be serve as our output. It's going to be the reconstructed image. And hopefully it can kind of exclude those undesired corruptions, and only the true images remain. I mean, the best estimate is remain. Okay, so someone may say, okay, in your formulation, your transform is unknown, your sparse code is also unknown, and here your image is insane. I mean, does this really work? I mean, is this really as good as you claim? Yeah, I mean, why not look at some examples and to see whether this can give us empirical good performance. So this is the example I gave at the first talk. So I say, okay, here's an impending problem. Our CSL building is covered by our CSL student conference logo. Let's run the image impending algorithm based on transform learning and see what we can get here. So it turns out that we get the result not so bad. I mean, you can hardly tell the artifacts unless you look really closely. So normally in image processing, we use this PSR metric to evaluate how well the reconstruction is, the quality. So later you will see this many times, and pretty much it's the higher the better. So not only in the image impending problem, let's look at the most basic image processing problem, image denoising. So we have this noisy baby face with ID Gaussian noise, and we run the image denoising algorithm. This is the denoise result we have, and pretty much we remove most of the noise, additive noise there, and we get much cleaner face here. And actually, our method can kind of compete with most of the popular and state-of-the-art method. And here I show a list of the competing algorithms. And for those who are working in this field, you might have already noticed some of the famous names here. So, well, this is kind of like a demonstration, like the usefulness of our train transform as an image regularizer. Not only image processing, we also realized that this transform learning can be used in medical imaging problems. So in the model imaging system, people normally wish to kind of reduce the runtime, reduce the system complexity, the radiation dose for CT, so that we can either have a fast imaging result, or we let the patient suffer less. But the problem is, if you directly recover from this undersample measurement without any additional regularizer, you get pretty low quality reconstruction, like the one I show here, by the naive zero fitting method. And this map on the right bottom, on the bottom right corner, is actually the energy of the residual error. So you can see by this naive method, you will observe a very high residual energy, which pretty much brings some troubles for the doctor to analyze later. So this is the result obtained by our group's previous work, which used dictionary learning to regularize the reconstruction result. And it kind of give us pretty good improvement in terms of reconstruction quality. But more recently, deep learning has become the trend and kind of pushed the limit so that it kind of produce a superior result comparing to the people call it the traditional dictionary learning, traditional machine learning method. You can see that the error has been suppressed significantly. But it turns out that our method can even beat the deep learning result by several, like 1 to 2 dB. I think the reason is because we have a more flexible way of imposing this regularizer, and because imaging system is not like image to image. You have to consider the forward operator imaging modality. So having better flexibility will be the advantage here in a complicated imaging system. And I just want to mention that this is ongoing work. We are still working on that to try to make an even better result. Okay, so we have covered like 2D data. So how about 3D data, like videos? So it turns out that the transform learning scheme can be very scalable to high-dimensional data. But the problem for video is that it's different from images. Like the batch learning algorithm doesn't make sense because no one wants to wait until all the data to be available, then start to learn. Like you want to have some learning scheme to be online to deal with the real-time data. So we come up with this online transform learning scheme where the transform will kind of gradually evolve as the new data come in and adapt to the most recent data with some forgetting factor or sliding window. So if you look at the atom of the learned transform, initially will be some fixed good analytical transform, but gradually it will evolve and you can observe the atom change which adapt to the most recently arrived frame or patches that will kind of reconstruct the most recent frame in the best way. And here's an illustration of the comparison between the clean example video, the noisy one, and the denoised result by, on the left, the VBM40, which was the state of the art, and then on the right is the result by our method. We can see that, you observe less artifact, from our result, both temporally and spatially. And if you take a closer look at that, so our result will preserve more, the texture details and informations, even when recovering this video from a very highly corrupted, noisy measurement, while the competing methods will be very likely to kind of over-smooth the edges and corners, which sometimes you may miss some important details. So that's it. So the take-home message, this talk, we are pretty much we're trying to show that the image model is very important in this ill-posed problem. And the transform learning is awesome, and let's let the data speak for themselves. And the transform learning leads to state-of-the-art results in image recovery problem. And yeah, that's it. I'm ready to take questions.
Thank you, Bihan. So any questions for Bihan?
Here.
Okay. So my question is, how big are the dictionaries that you use for the P1 formulation that you showed?
The P1, right?
Yeah.
Okay, so first I want to mention there's a difference between the dictionary and transform, right? So the reason we call it a transform is the model is different because normally the dictionary we're talking about is the synthesis model, which we factorize the data into a dictionary and sparse code. Well, transform is different. You directly apply that, which is very similar to the classic way, like how you apply the wavelet or something else, right? And then back to your question. So in the P1, the transform size is pretty much depends on what your input data is, like dimensionality of your input Y, right? So you can make it larger to look at more regional information, global information, or make it smaller to look at the local structure. For most of the image processing problem, we look at small patches, like 8 by 8 or 9 by 9. So that will be the kind of size of the transform. I mean, you can make it over complete. In this case, it will be a tall matrix, so that your feature dimension can be even larger than that. But it depends on your application, I would say. Will vary from case to case.
Thank you so much, Bihan, again.
Yeah.